Hey folks, welcome back. In the last episode, we covered the early days of electromagnetic theory and Maxwell's equations, military radars during World War II, and what was eventually to become what we know today as ground-penetrating radar. Today, we're going to continue our coverage of the history of GPR, starting in the early 1970s until today. Our specific starting point will be about December of 1972, when the Apollo 17 mission wrapped up. Now, this mission famously carried the Lunar Sounder Experiment, a specialized GPR that probed the moon's subsurface down to kilometers of depth. This period of lunar investigations generated renewed interest in subsurface probing using GPR technology. The early 1970s, kind of coinciding with these space-age developments, saw a definitive start of commercial GPR. It was really a watershed moment driven by some key researchers who saw the terrestrial potential of this technology. And right around the Apollo missions, the first dedicated GPR company was formed in 1970. Geophysical Survey Systems Incorporated, or GSSI, was established by Rex Maury and others, and they began manufacturing their own GPR systems for their internal consultancy use. GSSI launched their first commercial GPR systems in, I think, around 1973. Their early systems typically operated in pretty low frequency antenna ranges, generally like 80 to 200 megahertz, and they quickly became the dominant supplier, kind of the only one. These initial commercial systems proved viable for civil engineering, archaeology, utility mapping, of course, and the mining industry. However, the technology was still pretty rudimentary compared to what we see today. These early GPR systems used large electronic components that were susceptible to temperature drifts and vibrational issues, all sorts of breakdowns. Crucially, they were analog systems. The data relied on electrostatic plotters or those old green CRT oscilloscopes for display and recording, meaning that they had absolutely no ability to digitally store data for later processing. What you see was what you got. The late 1970s saw GPR applications expand rapidly, especially in very challenging environments, largely due to Canadian efforts. The Geological Survey of Canada began extensively exploring the use of GPR technology, and their focus was mainly on understanding permafrost terrain in the Canadian Arctic, and for good reason. This research was spurred by proposals for pipelines to bring oil and gas from the Arctic south to the lucrative southern Canadian and US markets. And that generated significant interest in what we call polar engineering solutions for frozen soil environments. GPR proved very useful for serving potential pipeline routes, such as the one along the Mackenzie Valley in the late 1970s. So concurrent work was being done in the US on the Alaskan pipeline routes, which were led by Gary Olhoff at the US Geological Survey. Now, this fieldwork quickly revealed some severe limitations of the current technology at the time. Their equipment was super heavy, very bulky, and consumed a massive amount of power, making it pretty difficult to use in these remote environments. Things needed to improve for this technology to be at all practical. Specifically, digital recording was necessary to exploit the rapid advancements in the concept of digital seismic processing that itself was transforming the petroleum exploration industry at the time. This push towards digitization gave birth to a major Canadian player. In 1981, A Cubed Incorporated was founded by Peter Annan and others. A Cubed spearheaded the development of low-frequency digital GPR systems. Now, this technology led directly to the commercialized pulse echo systems that Sensors and Software puts out today. The widespread adaptation of digital technology in the early 80s, it was really driven by low-cost analog to digital converters, personal computing being popular. It marked GPR's entry into the digital age. This digital capacity transformed the potential of GPR data analysis. And remember, before digitization, GPR data was just interpreted on pieces of paper or strips of paper as just raw, right? What you see is what you got, and we drew lines on electrostatic long sheets. With digital recording, routine use of digital processing, interpretation, and display techniques, and all of this adapted from seismic reflection methods became commonplace. Processing techniques like frequency filtering, background subtraction, and even migration soon became standard stuff. This technological momentum led to a critical commercial step in 1988. A-Cubed spawned Sensors and Software Incorporated, and it commenced commercialization of the pulse echo technology developed by A-Cubed originally in the early 80s. So this period between now 1990 and 1995 saw the true explosion of the advancement of GPR, with many groups worldwide becoming interested. GSSI themselves saw strong commercial success during this time, resulting in its acquisition by Oyo Corporation of Japan. Simultaneously, competition grew from the emergence of MALA Geoscience in Sweden. Now, MALA was spawned from the Swedish Geological Survey roots, specifically leveraging the work that they did on borehole radar development, initially funded from nuclear waste disposal applications in the 1980s, looking for places to place nuclear waste in solid bedrock, and they needed borehole radar to map where fracture patterns might be. Instrumentation underwent massive miniaturization in the early 90s, making practical GPR systems small enough to be kind of carried on a backpack by about the mid 1990s. And of course, by then, the growing availability of laptop computers provided the necessary processing power and digital storage capacity to handle the recorded data, accelerating this market uptake. The increasing professionalization of the GPR field was also reflected in the formation of GPR user meetings, which began to be held every 2 years internationally, the GPR conference. I think it started in 1988, and it provides a forum for the leading players to share results and discuss new developments and problems in the field of GPR. But along with new technology, low component costs, all the other advancements came another problem. The three main manufacturers at the time, so GSSI, Sensors and Software, and MALA Geoscience, were running out of users. Until the late 1990s, GPR was exclusively the domain of geophysicists and academics, and there was only so many of those folks to sell systems to. So, manufacturers got smart and worked to simplify their technology, particularly in the utility mapping and concrete rebar mappings fields, so that relatively untrained users could successfully use GPR technology to map obvious targets. Now, these systems were low cost, had sometimes throttled capabilities a little bit, but they dramatically expanded the potential market for GPR technology. At the close of the 1990s and as the new millennium began, the exponential evolution of computer power drove the next leap forward for GPR, and that is 3D imaging and multi-channel arrays. Managing huge volumes of digital information rapidly became relatively easy with the computers you could buy at the time, and making the acquisition of data on grids to create maps and sophisticated 3D visualization practical for the first time. And this demand for speed and high resolution 3D mapping led directly to multi channel GPR systems. These systems arrange an array of antennas in a row, allowing for wide swaths of ground to be covered in a single pass. And we'll cover this in a later episode. This acquisition mode makes data collection over huge areas significantly faster and more efficient. MALA from Sweden was kind of at the forefront of this, producing the first commercial multi-channel system in cooperation with Witten Technologies from the United States. These array systems demonstrated their power immediately when they were invented, One notable early application involved using a MALA mirror array system to map buried utilities and create a continuous 3D radar image of the subsurface around the ground zero site just after the September 11th attacks in 2001 on the World Trade Center. Now, this effort, which covered tens of thousands of square meters, showed that imaging radar had kind of more in common with scaled down 3D seismic imaging than actually, standard radar GPR processing. The technology of multi-channel radar expanded dramatically from the early 2000s. By about 2004, an array system known as 3D radar, and they now call themselves Contour, was released. This system, commercialized from the University of Trondheim in Norway, utilized 32 or 64 bow tie antennas with a step frequency that's an SFCW transmitter. By 2010, most of the major radar manufacturers were offering some sort of commercial multi-channel GPR system, with antennas counting from just 2 antennas up to 64, primarily targeting shallow utility investigation and archaeology projects. Today, sophisticated arrays feature, 32 antennas arranged perpendicular to ensure, full comprehensive 3D results. From the lunar rover experiments of Apollo 17 to the multi-channel arrays scanning entire Roman cities in Italy to monitoring ice road thickness in the Arctic, GPR has established itself as quite a mature and really indispensable tool. The trend towards quantitative analysis, where the raw radar cross-sections are really rarely needed and the output is direct user-specific information like a snow depth map or the location of specific utilities, is just around the corner. The history of GPR after Apollo 17 is defined by the crucial transition from this heavy, bulky analog machines used primarily in sort of niche geological studies to what we know today, highly portable, reliable digital systems capable of providing rapid, high-resolution, full 3D that guides engineering, archaeology, and just safety around the globe. I think the journey is absolutely amazing. Join me next time. Thank you so much for listening.